So just as we stopped earlier, del operator 1 over h1 die u1, 1 over h2 die u2, 1 over h3 die u3. So in this case, in the case of cylindrical coordinate system, we know that h1 is 1, h2 is r, and h3 is 1. So if we substitute there, that means our del operator can now be written like this. That is E1 over H1, E2 over H2, del like this. And don't forget that that is if you don't want to use this comma, which is this type of vector form notation, you want to use the actual vector notation. That means del is addition. So that means unit vector along R axis divided by H1, that is, I've suppressed this now. I'm now putting this back. Plus the unit vector along E2, that is E2 upon H2, then removing that plus unit vector along E3, the E3 which is along Z upon this, and so that is the actual is what the situation where you suppress this unit vector is what we have here. So as I said, E1, E2, E3 are unit vectors along R, theta, and Z respectively. Now, our interest now is to find this, which is the dot product of velocity Q and Navier operator. Velocity is this, Navier operator is now this. Okay, because we are plotting it here, because this one is 1, that is this. This one is R, that is that, and this is also 1. So that is how we got that product. So if we take the dot product of this, what we now obtain? Dot product we call from your remaining mathematics. If you have a vector A, which is A1, A2, A3, another vector B, which is B1, B2, B3, to take the dot product means simply A dot B, that is the components A1 multiplied by B1 plus A2 multiplied by B2 plus A3, of course, that one is trivial. So we do exactly the same thing here, therefore. So that means it is this we use to multiply this. That is QR times what? Times di R. Q theta, that is 1 over R here. That is Q theta upon R times di theta. And finally, QZ times this. That is QZ times di Z. So that is our Q dot del operator in cylindrical coordinate system. Finally, there is another one that I want to mention, because there is Laplacian operator. The Laplacian operator is simply del squared. How do we write del squared? Del squared we call del squared operator. Del squared operator. The del squared operator, which we treated, is what? Del squared operator, if you remember very well, is what? Is 1 upon what? H1, H2, H3. Remember your linear coordinate system. H1, H2, H3 of what? Of, I think I've written it today. This I've written, so don't let me waste time on that. I've written this. So this is going to be di what? Di U1 of H2, A3, H1, okay, plus di U2 of H1, H3 over H2 so that is di U1 plus di U2 of di u2 of what? Di u2 of the other scalar product, that is h1 a3 upon h2 di u2 plus di u3 of what? h1 h2 upon a3 di u3. So in the cylindrical coordinate system, therefore, if we substitute for our h1 substitute, where h1 is what? Where h1 is 1, hz is 1, and h2 is r. h1 is 1, h2 is r, and h3 is 1. Okay, h1 is 1, h3 is 1, h3 is r, h1 is 1, h2 is r, and h3 is 1. Of course, in this coordinate system, our u1 corresponds to r, our u1 corresponds to r, our u2 corresponds to what? Our u2 corresponds to theta, that means this is theta, and our uz corresponds to what? uz corresponds to z, and of course dot corresponds to that. So in that way, that means del square operator can be written in cylindrical coordinate system as what? Del square operator in cylindrical coordinate system, which is del square in cylindrical coordinate system, cylindrical coordinates cannot be written as 1 upon what? It is only r that when 1 times r times, so the only thing there is 1 upon r into what? Into di r of what? That is r di r. I think I've written this before. I can't remember. So next plus di theta of what is left here is just 1 upon r of what? Of di theta. Of course, this one can pull out of it because it does not depend on that. It's only theta. So this one, if you like, you can throw it out. Then plus finally di z of this one is r times what? Di z. So that is what that operator will give you. If you like, one can expand everything. Now, if all these are made use of in our Navier Stokes equation, so the Navier Stokes equation now reduced to what? Our NS equation, in cylindrical coordinate now will be what? In cylindrical coordinate, this now will be the vector form. First of all, the vector form is the vector form, don't forget, the vector form is the q, the t is equal to minus 1 over rho grad p plus mu del square q plus 1/3 of grad the q. And don't forget, this one translates into what? This one can be written as, if you like, can be written as di q di t plus q times what? Q times Q, then follow the rest. Okay? So if you now substitute all that we have done today, if you now substitute for Q in cylindrical coordinate system, and all this we have done, grad, we have done that grad, we have done this, so we can now have cylindrical coordinate form. Component form. So along R axis, it can be written as dqr, because qr is the component along that, dt, I laugh. The reason is that you have to check that this is really correct. Perhaps I even give it as an assignment for you to prove, because you see, I used to teach this at 100 level in those days. That is in vector analysis mechanics 1. We used to call it there. You see, when, of course, you have done it in physics, you might have forgotten that when you are now finding acceleration, if a particle is moving round and round, so the acceleration you have to subtract from it is you say maybe v squared over r. That is the same v squared over r. It's the same thing. I used to give them to people in their students in 100 level to prove, because it is in physics that when a particle is moving round and round, it is moving round and round, and this separation is r, radius, and the velocity is v. So the acceleration with which it is moving round and round is acceleration along that is always of minus v squared over r, or at times you say minus omega squared r. I knew this thing a very long time ago in secondary school, so I'm not going to prove it for you here, but you may be asked to prove. It's the same thing. This is acceleration minus this. That is the breakdown of this. The result is because this is in cylindrical coordinate. You cannot just write this. It will be wrong. This will be subtracted from it, because you are taking into account of not only linear but curvilinear, which is circumferential motion. Velocity along the circumference, which is just this. Along the circumference. You must, if you don't, you will miss it. Well, if I were you, I would make sure I prove it. Otherwise, you might be asked to prove it under 30 minutes more. Or it may even be online. It may be online exam. Just we hope this will be resolved before then. And God will take control. So I'm quoting the result. So for along R axis, this is the result. It's minus 1 over rho di P di R. That represents the component around. This is very easy. How did I get this? How did I get this from this? Remember, from this, del operator is the seed. This is del operator. This is del operator in cylindrical coordinate system. Are you with me? And if I now put P inside, put P here, put P here, put P here, put P here, are you with me? Then this row that is answer is what we do. So what I'm going to use to multiply is what? That is what is here. And that is that. That's the component along. So what is the component of this along R? The answer is plus mu, that's same mu. But this transforms to what? This one transforms to, because of place, it is still correct if you put it as del square of Q of R. Because today I've established the meaning of del square in cylindrical coordinate. Just look at the expression there. Then next is minus QR over R squared minus 2 upon r squared of what? Of di q theta di theta. That is the equivalent of this. The equivalent of this in cylindrical coordinate system is this again. Del square of qr minus component of r divided by r squared. The point you use this to divide it, you get acceleration. You see something related to acceleration because you are still going to multiply by. Then you can see you are now finding the partial derivative of q theta with respect to theta, not with respect to r. You can see r squared is common to them. In those days, very easy. At time we used to learn it by heart. Now, I'm there to come to this now. So this aspect is what? So let's write that. But because this is the aspect that shows that is it compressible or incompressible fluid. If the fluid is incompressible, you are lucky. That means you should stop where I stop here. But if it is compressible, you have to put everything. Compressibility means this is 0, but it's compressible, so it is not 0. So let's do that part. That is also nu over 3. It's not difficult to do this. We have done it today. You know div q, put it, then graph of div q, and you know what del is in cylindrical coordinate. If that is done, you will get di r, because the component of this along r is di r. We did it for a rectangular coordinate system of what? Of div q. Of div q. You can find div q. It's not difficult to find of div q. So that is what we get. Div q, we have done it today in cylindrical coordinate system. Then what is left now is because if I want to add body force, if there is body force, then I will put the components of body force along r. So that completes the first one. That completes the first, but is pregnant with some things. Like, let me laugh again. Then you should be able to show this. So go back to your secondary school pieces. It's there. Then there are some strange expressions in it. Not really strange. This also came here again. I see it again. QR over r squared, and also another component which is not even part of a component along r came in, which is di of what? Partial derivative of q theta respect to theta. Please take note of this. I laugh. Then they look strange, but it must be shown. Let us go to the component along theta. Along theta axis, what happens? Along theta axis, the same thing still happens. So here, if you do it very well, it is not the components along theta. So that is going to be what? You get the q theta dt, c minus or plus. If you do the calculation very well, and it is this time around, you know, this one is minus q theta squared. For this time around, it will change to do it well, that is qr times q theta. Of course, all upon r is the same. If we are talking of component, if we are talking of units, the unit of velocity here is squared. If we are talking of units, this is the unit of this one multiplied by this. Also, we give you the same units of this. Velocity component is meters per second. When you square it, that is meters square per second. And if you come here also, this is meter per second times meter per second. Meter square per second square. Okay, divide by this. You get this meter square per second square. So it's except that this one is minus and this one is plus. Now let us come to this side. From what we've done today, you can see that I want to write the components of this. Don't forget, del operator along theta is 1 over r. So that means that again I write minus 1 upon rho. But because del in cylindrical coordinate system is what? It is di r 1 over r di theta di z. Because this is the expression which we have done today. Therefore, when I'm writing the components of this along r, along theta, this is what I will get. Along theta, di theta, along theta, this is what I'm going to use. So that is going to be minus 1 over rho and what? It will be different from this one. Then again, di what? Di p, di what? Di theta. It's obvious that if you put p here, if you put p outside, it will change this one to what I wrote here. This 1 over r of di p di theta. But the one we did here before, because what is here is just ordinary. So that is why it changes only to di p di. So that is that. Now we have treated that. Now we are here. At the second stage, we want to substitute for that. So again, that is plus, that is also the same, that is plus nu, that is that. Del square operator is similar to this. It's similar but in another form with see it. Nu into the same thing. Instead of QR, put what? Put Q theta. He still agrees with it. Instead of this, put Q theta. Then you see, when this one is QR, what we are using this time around is Q theta. So you are still not that. I'm just teaching you the trick that I used to use in those days, because you don't need to start counting everything, but just study the symmetry. So the symmetry that QR, so that means that will be what? Minus Q theta upon what? Over r squared. It's still correct. Then the only difference is that, see, this one goes with theta. So it's exchange is no robbery. Since this is Q theta, when you are writing QR, this one is Q theta. So when you are writing Q theta, replace this with QR. Replace that with QR. Okay? So that is plus, and the sign also changes. Instead of minus 2 over r squared, that is plus 2 over r squared. Q over r squared times di q. I'm not going to use Q theta. You can see you have to interchange. Exchange is no robbery. So that is di q r di theta. Then this bracket, let me now close it conveniently without lots of generality. So that's that. You can see there is still nothing to worry about. If you study the symmetry, it's very easy to remember, because you can see again. I want to write this part. There's no problem. The only thing, just remember that your nabla. To write this part now, to write this part, I will still get plus what? Except that, if you remember that nabla operator. Nabla operator is what? Nabla operator is now quadrant is di r 1 upon r di theta, abi, then di z. So this is the only thing you should remember. Because I'm writing, this is the component I'm writing. Di means, that means this expression that I want to write, r will come there. Unlike the other one, r does not surface there. R will come there when you are writing it, because of this situation. You can see this is just 1, because this is just di r of that. But because of this now, so this will be written as what? Plus 1/3 nu over r. You want I'm putting nu over r instead of nu upon 3 that we put here, because of this r. So that is why I'm putting that. So of what? Of di theta of again div q. we can restart. It will be too long if I start expanding because the Q here, you can always, we have done it. Just put it. Then the components of force along theta is now what? F what? F theta. That is if there is body force by unit mass.
Also, I have new over 3 and new over 1.
I'm very sorry that 1 over R. Thank you for that. So you can see new over 3. See, so this F theta is body force along theta axis and it is per unit mass. Take note of that. Of course, we can write the third one. The third one along z axis is very, very simple. It is in cylindrical coordinate system. The problem is along R, along theta. Along z is just like a rectangular coordinate system. So let's write that. The components, because I want to write the components along that. It follows the same framework because there is no circular motion along z axis on like along the plane. The circular plane perpendicular to z axis. So along z axis, the axis of the cylinder, we have again, that is d what? dq along z, dt. So it is free of this. It doesn't depend on this. You know, these other two that I underline, it doesn't depend. And I forgot also that, of course, I've taught you the trick to get it. That if you get this one is obvious. So this again, there is nothing to be added to it in its own case. That is why it is simpler. So this is equal to, but again, it looks like this because like R, HR is 1. You can see nothing multiplies it here. So exactly the same thing. So when you have this, that is minus 1 over rho di P di Z. Okay? So that's that. Clearly we have gotten to that stage. Now we are now here. Plus mu of what? Into, again, it's very easy. It is, that's why I tell you the simplest. Of Q along what? Along Z. So all these sub, they are not there. They are not there in its own case. This and this, they are not there. Because QR is 0 there, Q theta is 0 there, when in that and so this is the only one. This one is very much simpler and it looks much like that of rectangular coordinate system. Now, what is left now is what? The incompressibility part. The incompressibility part is now what? This part. So this part is now what? The incompressibility part, just add, that is plus 1/3, just like other, 1/3 of, that is mu upon 3, di z of what? Of the q. Then, it's simple, you can see, it is just like the other one that we had here. You can see because of the fact that the scalar factor is 1, 1, it's just like this. Then plus if there is body force, F what? Fz, body force per unit mass along the z axis. So the three corresponding equations, along R, is along R, which is this, along R. I think we have gotten it before, which is the QR T minus Q QR, so Q theta squared all over R. Is it R squared? It's R, not R squared. So this is the first one, the first equation for cylindrical, this is the second for cylindrical, and this is the third for cylindrical coordinates. They are the component form of Navier Stokes equations. These equations are very important because those of you who may be falling on in fluid, in most cases, there are serious research work going on cylinders. People have almost exhausted that of a rectangular coordinate system. There are serious research work going on cylinders and spheres. So that is why these formulas, they are very, very important. And if you know it, just quote. That time nobody will ask you to prove it. But at your level now, you may be asked to prove. But then you can quote and use and continue with your research, because people have derived it. You have done it in the class. You are gaining nothing to start deriving that any longer. It is the usage that are important at that level. Or except if you have other new things that you have derived that people have not derived before, then you carry it on and continue with your research. And then let people know. So these three equations are very relevant. And we have similar equations in the case of sphere. So those are the three cases I'm going to teach. Then the rest, those of you following in the sense that those who want to specialize in fluid dynamics, you will need to read further. But since we have put you through the background setting, you can always proceed on your own. Now let me quote, without loss, let me quote that of similar results. But don't forget that if the fluid is incompressible, of course, this will go for incompressible fluid. So the equation becomes simpler. Because I saw compressible problem last in 1984. It is published in one of these European journals. Although it is with my Oga that time, with Adeni and Bacha, 1984. It's compressible fluid in plasma. If you are interested, you can browse. If you browse my name, as of that time, you see the paper there. But I was trying to join the crowds, because we join crowds, they will say you have many papers. But because it's not easy, a paper under compressible may take you 6 months to finish in those days. But now with the use of computer, if you are serious, within 2 or 3 months, you've settled it. So let us write the equivalent in spherical coordinate. In spherical coordinate, because those 3 coordinate systems are very relevant. Like spherical, like we have something like a bomb inside the ocean, and it's spherical type. When it is exploded, yeah, we may want to solve that problem, but as of now, we are still building the knowledge. We are still building your knowledge, so we don't need to bother about that. So those shapes, they are very relevant in life. Or nanofluid. Nanofluid, some nanofluid particles may be in form of spheres, some may be in form of cylinders, some pellets, some in form of rectangular shape. But when all these shapes are well known, do not be afraid to solve problems related to them. The spherical coordinate form of Navier Stokes equations. Don't forget that the velocity Q in spherical coordinate system is r theta r what? Phi. Of course, it's easy. It's just like the shape of the earth. When it is like the earth, the shape of the earth, something like this, having the shape of the earth. And then you pick any point of it. This is the center. Pick any point. This is x-axis. This is y-axis. Y-axis. X-axis. Z-axis. Then it is quite possible to pick any point on the sphere. If you pick any point of the sphere, if this is origin, say, you pick any point on the sphere. This is a patch. A patch on the sphere. Then, if you locate it down to this, and you trace this, and you trace it also up, then what we are saying is that the motion is such that this angle is theta. Theta is between what? 2 pi. Just like your longitudinal movement on the surface of the earth. And the other one is, this one is phi. Just like latitudinal. It says latitude 0, latitude 30. Are you with me? And latitude varies from north to south. So again, this one is 90 degrees. 0 is less than pi, is less than equal to pi, 180. Because 90 of not theta. So if this distance from here to the patch on the surface is r, then that means the position vector of this thing, which was the position vector of this, which was formerly in terms of x, y, z, cannot translate to what? It cannot translate to the vector r, theta, phi. That is cylindrical coordinate system. In cylindrical coordinate system, see, velocity is, you can see, this is wrong. Velocity is component of velocity along r, component of velocity along theta, component of velocity along phi. Don't forget. Then the position, if you write this as a position vector, the position vector, if I write it as r, or some people may write it as L vector, it represents what was here before, r, theta, phi, in terms of components along that. And also, another important thing is that what is Navier operator in this, because when you are transforming it, what is Navier? Navier is, in this case, Navier is di-r. Because under this situation, in spherical coordinate system, hr is 1. So you see, 1 over hr times di, then h theta, which is 1 over h theta in spherical coordinate system is r sine phi. Phi is the angle that varies between 0 and 180, because sometimes they will put this as theta, but they will explain that theta is the one that varies between 0 and phi, and they may change this one to phi, that it is between the, but that should not cause any confusion at all in this time, in as long as you know the variation. So, but it is easier to explain the way I said that this one is standing for latitude and the other one is like longitude. So in that wise, if those tell you, you put this one as h phi is equal to r sin theta, but don't bother. And the last one, h along that is, no, it's r. It's r. It's r. Yeah, I have told you, I said, usually this does not agree with this. If in some textbook, if they write this one as h phi, they will now say sin theta. Take note of that. Don't condemn the book. They didn't make mistake. It is just the perspective you are looking at it. If you look at it in my own perspective, it's fine. Then in that case, they will now change this one to h theta. They say h theta is equal to r. Fine. The only thing you should query is how does theta vary? How does phi vary? If you know how theta is varying, you know which is which. If you know how phi is varying, you know which is which. So we don't use to query on that. Even in mathematics generally, we don't bother about lettering notation. Letters are dumb. You can use anything. In as well as what you are talking of is mathematics. Just accept it. Now, so in that way, that means I will write this as what? Del operator. So that del operator now will be what? That is 1 upon what? R what? Now it is this. R sin what? Sin phi. Because of the scalar factor. Okay, di what? Di theta. And for the last one, I want to write di phi. What is the one scalar factor? That is 1 upon r. That's it. Then follow the same trend. You don't need to waste time on this. When you sit down on your own, you'll be able to arrive at all this easily. But it's always good if you want to understand mathematics well, do it yourself. Try to be sure. Nobody is perfect. At times I can even along the line when I'm teaching, I used to make mistakes like this. This is very obvious. This is what I wrote. Although I was fastly thinking of position vector. So it's something I was thinking of. It's another thing I wrote. Nobody is perfect. Now I need also del square, because del square appears in the expression. We need this. You don't have a problem with the result of it. You need this expression as well. Okay? Then what would this be? It's easy to get the Q, since you already know this and you know Q. So you can always do that on your own. So don't let me waste time on that. So what is left is now this. After del squared, I will now quote everything. So after del squared, the result now follows. So del squared also, to follow that transformation, I wrote it today, which is 1 over h1, h2, h3. If you multiply, so if you multiply and simplify, open the bracket. Of course, h1, h2, h3, under this situation will be what? R squared sine phi. Multiply them. Multiply the 3. Use this to multiply this. Use it again to multiply this. This is what you get. Then and simplify. If you simplify that, you throw it, you know, this is 1 upon that. If you throw in this thing and simplify it, that's good. It's good not to. Then this will give you 1 upon r squared di r. Okay, you saw similar thing like this in the cylindrical coordinate. But this one is r squared of what? Di r. That's what you get. You can see we arrive at this. But you see this one, this one is here. But because this also involves sign, came out to destroy it. That's it. Because if you look at what is here, this is supposed to be di r of what? Of h theta h phi over what? Over h r of what? Of di r. If you follow that our trend, this is supposed to. But how do you simplify this? I don't want to, because of I think I'm too general to students these days. A theta is what? This is di r. A theta, c there is d there. A theta is r what? R sine phi. That's h theta. Then h phi is what? It's also what? R. When you multiply. No, there is an error. This one is 1. That is r. H phi is r. Okay? A theta is this. So when you multiply, what do you think? That is r squared. R squared sine phi. That's good. Then you divide by HR. HR is 1. Then you divide it by 1. It's theta. So now di r. I don't want to treat this first one because I'm too sympathetic these days. Because everything depends on R. This does not depend on R. It can come out. Don't forget, you have 1 upon what? 1 over h1. If you multiply everything here, it's going to work. So, if we expanded and this one comes out, this will cancel this. That's the result of this. Just to, I don't feel, let me assist. So, but because many students this day, I don't know. Many of you are busy nowadays, I don't know. But since you want to be masters of mathematics, you cannot tolerate that again. You've tolerated you at undergraduate. You cannot do that when you want to say that you master a course. You, when you master a course, you must be organ in that course. Master. Organ means master. So, that is how we got that. Then others. Let me follow the same trend. The next one now will be, because of this same something, the next one is going to be 1 upon r squared sine square phi. Okay, that's what we're going to get. Then there 2 theta squared plus, lastly, the last one, which is going to be 1 upon, take note, r squared sine phi. This one is squared, though. This one is 1. Take note. So, of what? Of di phi, of what? Of sine phi, di phi. That's the expansion of this. You know, I didn't put this factor. I've already simplified. You can actually simplify because it's 1 over. So that has been simplified. So if you do that, you get that. It's even good that I didn't code that so that you'll be able to sit down and see that it will only give you the first one I've already shown you how it is. Then you should be able to show the rest when you expand that factor inside. I mean the denominator factor 1 over 8 times 3. So that is that. So when you use that, I think I've used this only to explain. You see how we got that. So that is the equivalent of del square. And those are the things you need. And in this case, what is going to be your d dt? If you expanded your d dt out, which I've shown to you earlier, d dt is what? D dt can be written as what? D dt can be written as di dt plus q dot grad q. That you can simplify, but if you do it well, this is what you are going to get. QR di r plus q theta upon r sin phi. It's obvious. If you remember their scalar factors, d theta, and finally we have a q phi upon r di. So that is the expansion of that. This is this one is in consequence of what? Of q. That one is as a result of that. Now, without loss of generality now, we are now free to state the NS equation component form in spherical coordinate system. So in spherical coordinate system, therefore, for a compressible fluid, we can write along R axis. So we have dqr, theta, that's acceleration, minus q theta squared plus q phi squared. You can see in cylindrical coordinate system, this theta squared also came in there. But because this one is spherical, all these angles are important. Theta and phi are equally important. So this again will be divided by r. If this one were not there, this one will have given you what you got earlier in the case of a cylindrical coordinate system. Now we have written that. Now I want to write this part now. 1 over this grad p. You know that is equal to that. So when that one is written, it doesn't change for r because hr is 1. So there's no problem on that. So this is just minus 1 over rho by p. Please take note because of careless learners. This minus is on the same line as this. That means this minus is for this. This is not minus. Some of you used to be careless, but you try to observe your lecturers. You have to minimize careless writing. This minus is for the whole thing. So it is not this one that is sharing it. Because I know many of you are very careless. When they're studying in the class and I go to where you behave, you pretend at times, I see. But if it is the class, I know when I used to move around, when I move around, and some people will put minus there. That's why I'm worried because this is electronics learning. Now I need this part now. I need this part. The component along R. So again, I don't need to waste time on that since we have done similar things under cylindrical. That is that. Now this, you can always do it. I've done the expression too. This del squared operator. In spherical coordinate system, so again it is similar, almost similar to that of the cylindrical. So this is because this is own del square. It's different from that of the cylindrical. So I'm now putting this del square here. So that is del square of what? Of the components QR, okay, minus 2 QR upon R square. If it was cylindrical coordinate, if you remember, it was minus QR over R square. But this one is minus 2 because it depends on its derivation. It is this derivation I want you to show. Please show it, oh. And I will not say this. So that is why I was brought up, and I want you to be very good like me as well. So next, minus. This is a bit longer because of two angular relation. But 5 also upon R square. You can see this expression is not in order because 5 is 0. Continue is 0, so this part is not there. And still continue. After this, you can open the bracket, I have not yet closed it. Then next, minus 2 upon, let me continue. Minus 2 upon R squared. Again, Q theta came in again. Just I did in the other, but not the derivative. So that is Q. The Q theta came in. The opposite of this. That what? That theta, but this related to theta. Again, minus 2 upon R squared sin 5 times partial derivative of Q 5 came in again because these are the two angular motion there. It's an angular movement there. So that is Q partial referred to 5. At this stage, you can close it. You can see it has, apart from this, it has additional 4 components. 1, 2, 3 added. Unlike the case of spherical, it has 3. Now, we want to write this part now. The other part now that is left is now what? Over 3. Isn't it? Grad what? The cube. So, that can actually be good because it's very easy for you to do this, to be too long. You have done it. So, I will just put the components of that. So, that is plus this time around, and that is new upon 3. But the scalar, that is R sin 5. Because you multiply by the scalar underneath. That is R sin 5 of what? Of, I hope I have not made a mistake. Yes, for the arrow, it doesn't have R in its own place. Because HR is 1. HR is 1. Because HR is 1. So it is just 1 over 3. It is mu over 3. Because its own is 1. I will have multiplied by that. So times di-R of what? Of the cube, which is easy to get. Then, if there is a body force per unit mass, then we add what? We add F what? F along R. That is the component of body. It's not always very important to put that because you can always add it at the end of the day. Please try to take note of the geometry. This bracket open here and I close it here. Take note. Now, how about the components along theta? The component along theta for this the component along theta, the Q follow the same trend. So along